Welcome back, students. Right now we're going to be talking about measures of center and variation. So first let's talk about what a measure of center is. A measure of center is a measure that represents the center, or the typical value, the normal value that we would expect from a data set. The mean, median, and mode are all measures of center. They are trying to get at what is the middle, what is normal, where is the center of this data. That's what each of those are really trying to get at, just with different methods. So the mean is the sum of the data divided by the number of data values. So in other words, if I have two numbers, 4 and 5, the way to get the mean of it is to add them together and divide by 2. Now that would give us 9 divided by 2, which is a 4.5, which, remember, this is a measure of center. Think about what is directly in between a 4 and a 5. Well, 4.5. Okay, and this is the approach that a mean takes in finding what is the measure of center. The median uses a slightly different method. If my numbers are 2, 3, and 4, the median looks for whatever number is directly in the middle. And that's how it is defining what is the measure of center. Now, if there is not a number in the middle, such as our example with 4 and 5, it then finds the two middle numbers and it simply does the mean of those. So we do 4 plus 5 is 9, 9 divided by 2 is 4.5, just like we found before. Okay, a mode is whichever number or value repeated the most often. Now there can be more than one mode. If you have multiple numbers that all repeated the exact same number of times, and so there's not one that repeated the most, but there are a couple that repeated the most, then you can have multiple modes. So let's go ahead and let's start with calculation. In your 9th grade year, we are less focused in on your ability to perform this calculation manually. I don't need to see it written out, pencil and paper. However, what you should be able to do this year is to learn how to interpret them. But in order to interpret our numbers, we still need to get them. So what we are going to use is a nice fast method. We're going to use a calculator. I've opened up over here Desmos. So in Desmos, I'm just going to pick some letter. Let's say A. Say it's equal to, then I'm going to use the square bracket. And now I'm just going to type in my list. So we've got the student quiz scores, 95, comma, 100, comma, 90, 90, 95, 10. And then end that square bracket. And I've got my A is a list with 6 elements in it. Well, now, Desmos is going to do a lot of the work for me. If I type in mean and then I put A inside, it has now calculated for me exactly what the mean is. Now when we write down mean, a lot of times we'll simplify it by using X with a bar over it. So this is to say the mean. And our mean was 80. Okay, if I want to find the median, type in median, tell it what list, it'll organize it all and then figure out which number is in the middle, and we've got a 92.5. All right, so I'm just going to write over here now, median was equal to 92.5. It will not calculate the mode, but just remember, mode is whichever number repeated the most. Let's see, 90 has repeated, and 95 also repeated the exact same number of times. Therefore, our mode is 2, a 95 and a 90. All right, so next we want to talk about which measure of center best represents the data. Okay, now this is where we're really starting to talk about something new. Calculating mean, median, and mode, you've probably done that in the past. When we're talking about what is going to be the best, I want you to think about grades and how grades will many times work. Let's say that there is a student who got a 100 on a test, a 95 on a test, and a 90 on a test. So he's had 3 tests. He's aced all of them. Okay? He's done a great job. So from that, if we were to find the mean of that data set, the mean would be a 95, and the median would also be 95. Okay, if these were the numbers we were looking at. Now, if I used those same numbers and did something interesting. So let's say there was a 4th test, he got a 0 on it. All right, so the median is now going to change. We just have to find the average of 90 and 95, which is just going to be 92.5. So the median didn't change much. If we then recalculate the mean, so let's do B is equal to, and let's use those numbers, 100, 95, 90, 0. Let's find the mean of B. And all of a sudden, it's dropped all the way to 71%. So notice the way that they changed all because of one single number. The median did shift, but it only shifted a little bit. The mean, however, shifted a lot. That one bad test score really tanked his grade. It went all the way from an A down to a C minus. So this little change right here influences what we say is best. Remember that with measures of center, we're trying to talk about what's normal, what's average. So if we were to look at this student and try to identify what caliber of student is this? Is this an A student, a B student? What caliber is he? To me, this looks like an A student who had one bad day, who just had that one day where he got a 0, and heck, maybe he was absent that day. That 0 seems really odd and out of place. So that 0 is what we'd call an outlier. When you have one number that is so far away from the rest of the numbers, away from the grouping of the numbers, that you feel like there's something odd going on about it, that's an outlier. And we've got more formal definitions of how to determine whether or not a number actually is or is not an outlier. For right now, we're just going to use the definition that it's a number that's far away from the rest of the grouping. And if we look at this data set, we do have an outlier. That 10%, everything else was 90 or above. He had a single bad test score in there. So I'm now wondering, did his girlfriend dump him the day before and now he's eating Ben & Jerry's on the couch and not doing any homework? And maybe once he gets over it, his test scores are going to go back up. But that test score is weird, and I don't know what happened there. but do I really feel it should be affecting his grade a lot? Now, of course, in school, they're going to use the mean. You don't get to pick and tell a teacher, I want you to use the median. You don't get to pick that. But I would say in this situation that the median is the better representation. Okay, the median representation. The median really shows his quality better, okay? Because that outlier is going to drag the mean down lower than is what is actually normal for him. Normal for this student is to be in the 90s, and the 10 was a fluke. But because that 10, we're going to assume that far lower scores are actually what's normal when it's only one bad score. That's what makes median the best. So, something to keep in mind. We use the mean when there are no outliers. That's when mean is the best measure of center. We use the median with outliers. Okay, and then off to the side, we haven't been talking about it, mode. Mode is kind of this weird one where it's almost more like when we care about what's popular. I'll use mode a lot with categorical data. When we look at what was the largest bar of our survey of what's your favorite food, I can't add a pizza to a hot dog, divide by 2 and get a chalupa. Okay, it doesn't make any sense to do that. So when what we care about is what was the most popular answer, that's where mode comes into play. And there's other places where they've used mode numerically, such as golf, to determine par. But for the most part, we will look at situations in which the bigger decision is between mean and median. So when we remove an outlier, so we're going to use the same data as we had before. We want to identify the outlier. Well, we did. And we want to figure out how it affected the mean, median, and the mode. So what I'm going to do is come back to my data set, and I'm going to go ahead and I'm going to go over to the 10 and delete it. And now we can see how that has affected our mean and median. 94, 95. Okay, and the mode didn't change at all because we didn't delete either of those numbers, so the same numbers were still repeating. So let's look at both of those. The mean before had been an 80, and now it's a 94. The median before had been 92.5, and now it's a 95. And the mode is completely unchanged. So removing the outlier moved the mean up a lot. Removing that low median moved the median up a little. And removing the outlier did not change the mode at all, because the mode is about what number repeated the most. If it's repeating, it's probably not an outlier. So the mode will largely be unaffected by removing something such as an outlier. Okay, but do note once again that if you have a low number for an outlier, so one number that's way below all the rest, removing it is going to move these numbers up. If our outlier was way above everything else and we remove it, that's going to lower all of the numbers. Okay, and once again, mean is what's going to move the most, which is why we tend not to want to use mean with outliers, because the mean is pulled so far in the direction towards the outlier. All right, so one explanation for that outlier Like I said, let's go ahead and go with the example of his girlfriend dumped him and his world is slowly spiraling, and his self-esteem is crashing, and he doesn't know which way is up anymore, and he spends all of his nights not doing homework but eating lots of Ben & Jerry's ice cream. Okay, and so for that reason that week, he didn't do well on his test. Okay? But there could be other explanations. But that's just it. An outlier can many times be explained by, well, there was an odd situation. Something not normal caused this variation to happen. So now let's talk about measures of variation. So rather than trying to find the center, we're talking about how spread out the data is. Okay, is all the data clumped together into a small area, or is it very spread out? We've got two measurements that we are going to be using right now to measure variation. One of them is range, and the other is standard deviation. Now, the range is just the difference, meaning subtraction, of the greatest value from the least value. All right, so that's all you have to do to find range. It's going to tell us how wide the entire set of data is. So we've got two reality cooking shows, have 12 contestants each. The ages of these contestants are shown in the tables. We want to find the range of each result and compare it. So I want to find the lowest number and the highest number for each of these. Let's see, there's a 19-year-old and there's a 48-year-old. All right, so show A, all of their contestants have been somewhere between 30 and 19 years old, meaning they've only got an 11-year gap. So for some reason, this show does not like old people and will not have old people in their show. I mean, notice the range is only 11 wide. And you're starting in like at 19. So that's very limited range. B has ages from between 48 and 19. All right, so that's going to be about 29. So this show looks way more inclusive and less ageist. That show looks like the one that doesn't care if you have a few gray hairs. Okay. Now, part of the problem with us doing that kind of analysis with range is fairly limited in that it ignores all the numbers in between. We only used two numbers to calculate how much variation was happening here. And so it may not give us the best image. So, for example, we say that data has very little variation if it's got kind of this tall, thin peak when we graph it. Okay? And so we could have this data that looks like it's got a very small range, but that one, if both of these represented the same number of people, this one, sure, it crammed everybody right in there, but the range would be the same as this one. And that's part of the trouble with only using the range is we're not getting a full feel for how spread out the data is. We're just knowing the biggest subtracting from the smallest. So that takes us to another way of measuring how spread out the data is. It's called a standard deviation. Here's our monstrosity of an equation to calculate a standard deviation. I will kind of walk through it A standard deviation of a numerical set is a measure of how much a typical value in the data set differs from the mean. So right here we've got our symbol for standard deviation. It is read as sigma. Okay, that's how you pronounce that symbol, sigma. In this equation up above, we see the x bar, that's supposed to be the mean, and where it says x1, it means we're taking our first number from our data set, subtracting the mean. Our second number, subtract the mean. And we're going to subtract all of our numbers from the mean. Then we're going to square them. And then we got n. N is the number of values in our data set. And the deviation of a data value, x, is the difference of that data value and the mean of the data set. So everywhere you see the x minus x bar, or the mean, these are all deviations. Okay, how far away you are from the middle is how much you have deviated. Okay, so a small standard deviation is going to mean that all the data are clustered around the mean. They're close to the mean. A large standard deviation means it's more spread out. Now, maybe that was kind of hard to understand. So let's look at it in use, in how it would be calculated, and hopefully it makes more sense. Now, bear in mind, I'm going to walk through the calculations right now, and we're going to do them step by step. For the most part, I would not do this by hand. In the future, I will have you using a calculator. I do it by hand right now because I want to show you the process so that it makes more sense what it is saying. Okay? And so that's why we will do it this way right now. So we're going to use show A from example 3 in order to do this. So first thing we need is we need to calculate the mean of show A. So I'm going to go ahead, I'm going to bring up my Desmos again. And let's go ahead and we'll just change A. There we go. Okay. So for show A, 20, oops, 27, that should be 29, 20, 31, 12 element list, that looks good. And the mean is 25. All right, so just calculated my mean. So I'll come back down here. The mean was 25. So we added them all up, divided by 12, and we got 25. Next, we would want to calculate all of the deviations. So what I'm going to do is take a look at all the numbers, and we're going to start subtracting them from 25. So let's do this. All right, so now I've got all my numbers written out, and all I'm going to be doing is subtracting the mean from each of them. What I am doing is I'm trying to find out how far away all my numbers are from the mean. And that is what we call a deviation, how far you are away from the mean. All right, so that'll be -4, 3, -2, -4, -5. Oops, looks like I made a few mistakes. That should just be 4. That should have been a -3. I don't know why I started messing up like that. That's kind of silly. 6, -5, -6, 0, 2, 5, 6. All right, so those are all of our deviations. Now, a standard deviation, in the end, is really kind of getting at what is the average amount to deviate? What is the average amount to move away from 0? Now, a lot of people might be tempted now, well, if I really want the average of my deviations, I could just add all those up, divide by how many there are, 12. If you try to do that, though, the mixture of positives and negatives is going to give us a 0. So what we're going to do now is square all of our deviations. So we would have 4 squared, -3 squared, 2 squared. And I'm going to get all this written down. All right, so I've found all of my squared deviations. Okay, so I just squared all of them. And notice they're all positives now. So now that they're all positives, what I'm going to now do is find the mean of my squared deviations. Well, finding the mean shouldn't be too hard. I can come over to my trusty calculator and I can go ahead and just change those numbers again and allow it to do all that work for me. So 16, 9, okay, and it looks like I may have lost some. All right, I found my missing numbers. Okay. All right, so the mean of this would then be 19.3. So great. Our average of how much they deviate is 19.3. Oh, but wait, we squared all these, so all these numbers are artificially high because we multiplied them by themselves. So we want to get that number back down, so we're going to take the square root. A square root undoes squaring, so we're going to take the square root of 19.3 RT, and we get approximately 4.4. So on average, the age differs by about 4.5 years. So all the contestants are about 4.5 years apart on average. That's not a huge variation when we're talking about ages. So we can see all of the data points are very close together. This is a very accurate way of measuring the variation in a data set because we use every single number. Every single number affects this average. Okay. Now let's quickly talk about transformations. So there are certain things that may happen to a data set that you may need to do. So let's give an example of a teacher gave a ridiculously difficult test. Everybody failed it. And so the teacher now wants to improve grades by saying, all right, I'm going to add 20 points to everybody's grades. So that would be applying a transformation to the data set. Okay? And we want to know when the teacher does something like this, how does that affect our different measurements, our measures of center and our measures of variation? So a data transformation is a procedure that uses some mathematical operation, like adding 20 points, to change a data set into a different data set. So if you are using addition, when you add some number k to each value, the measures of center of the new data set can be found by just adding k to the original measures of center. So if all of my numbers are 20 bigger, well, then the average is going to be 20 bigger as well. Okay? The median will be 20 bigger as well. The mode, all those repeating numbers will all be 20 bigger, but they'll still be repeating, and those will be 20 bigger as well. The measures of variation of the new data set will be exactly the same. We did not change the variation by adding a number everywhere. We moved all the numbers up, but variation is a measure of how spread out they are. We didn't make one student further apart than another. A student who scored 1 point higher than the kid next to him still has scored 1 point higher after we add the 20 points to everyone. So the variation has not changed. Those numbers will stay exactly the same. When you do this with multiplication, however, each value in a numerical data set so it's going to get multiplied by the number k, the measures of center, mean, median, and mode can be found by multiplying the original measures by k. All right, so we would multiply all of them. So measures of center and variation. So whereas variation stayed the same when it was addition, in multiplication, it will also be affected. Okay. All right. So we've got this. Notice these are the same test scores that we had above. We have already calculated these. So we are going to find the mean, median, mode, and range and standard deviation if I curved the grades by adding 5 points to everybody's grades. So we want to know mean, median, mode. Remember, these are the measures of center. And then the range and standard deviation. Okay, so for a lot of these, it's going to be pretty easy. Remember, we're adding 5 points to all these measures of center because we're just adding, will just be 5 more. So we would just add 5 to all of our original numbers. So 80 plus 5, 92.5 plus 5, 95 plus 5, 90 plus 5 to get all of our new values. So our new mean is going to be 85. The median, 97 now because we added the 5.5. The mode had a 95, which then changes to 100, and a 90, which will now change to 95. I just added 5 to all the numbers we had already found. Now, as far as range and standard deviation goes, those wouldn't change. So I could even go ahead and just find those numbers for the original data set, and that would help me to know. So 95 all right, so we've got mean and median in there, but we need another thing. So I'm going to come over here to functions. I'd click on stats, and so one thing I know I want is the standard deviation. So let's find the standard deviation of A. Notice how much easier that was than what I did in the previous step. So about 34.49. Well, we added 5 to all of those. Doesn't matter. Okay. 34.5. Standard deviation, even after we add them. Remember, we just moved all the numbers higher, but they're still the same distance apart. Okay, so the standard deviation wouldn't change. Let's quickly see if we can find something for range. Well, we do have a max and a min, so let's do this. The max of A minus the min of A equals 90. So our range is going to be 90, because the range and standard deviation from that won't change just from adding it. But let's say we were altering grades by increasing each score by 10%. In order to increase them by 10%, that means we're going to multiply by a 1.1. So, according to this, we would just multiply all the originals by 1.1. So our 80 that we had originally, we'll multiply it by 1.1 to increase it by 10%. The 92.5, we're going to multiply it by 1.1. The 90 and 95 of the mode, both of those are going to get multiplied by a 1.1. And now this time, even the range and standard deviation, and 34.5 times 1.1. I'm just going to multiply all of them. Mean, median, mode, and let's see, and actually both of those were mode, range, and the standard deviation. Okay, and that's how I would find that transformation. All right, I hope that helps you with your work. Good luck.